Hello, this section is section 2.6 on higher order derivatives. So let's just jump in and we'll take an example of a polynomial function. Here I have the polynomial function f of x. I just kind of picked this randomly, various coefficients and powers of x. So we can take its derivative. So I'm not going to go through all my intermediate steps, but you can check f prime of x is going to be 24x to the fifth minus 12x to the third plus 3x squared minus 1. Great. So we just took the derivative. But here's the thing we want to keep in mind. When we take the derivative of a function, this is a function, right? I now have this new function with a new formula. And if I have a function, I can think, what does its graph look like? Does the graph have tangent lines? Of course. Can I figure out the slope of those tangent lines? Probably. Can I think about the rate at which this new function is changing? Sure. So to answer some of those questions, I would want to think about the derivative of this derivative I just figured out. So if we do that, that's called the second derivative of f. So the idea is I started with plain old f, right? Here's my original f. And this is what is now sometimes called the first derivative, f prime. But I can take another derivative, and we write that with 2 primes. So f prime prime just means the derivative of f prime. So if we go through that, we would have 120x to the fourth minus 36x squared plus 6x. If I start with f and take the derivative twice, this is what I get. This notation here in the middle, that's just a different notation for second derivative. You will never need to create that notation, but you should be familiar with it. You should be know it well enough that you recognize it if someone asks you about it or uses it. And we can keep going. Right? Here's my second derivative. If I take another derivative, that's called the third derivative. And we would write f prime prime prime. Usually we say f triple prime. And I take another derivative, and this time I get 480x to the third minus 72x plus 6. And we can keep going. Now, here's the thing. 3 prime symbols is our limit. What we don't want to happen is if I want to take the 11th derivative, we have to go f 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then someone else has to come back and look at that and count how many primes there are, right? It gets ridiculous after a certain point. So we say the maximum number of primes we will write is 3. And after that, we just count how many there are and we put it in parentheses. So my fourth derivative, I've stopped doing primes and I'm just putting the number 4 in parentheses as a superscript, right? That means pretend there are 4 primes there. So I've taken yet another derivative. I get 1,440x squared minus 72. The fifth derivative, again, once I get past 3, we're just putting the number in parentheses. And I could keep going, right? So theoretically, we could do this forever. Very often, at a certain point, it stops being interesting. But this is how it works, right? So really, we just have this verbiage of second derivative, third derivative, etc., and some new notation. But if you know how to take derivatives, you know how to take second derivatives and third derivatives. You're just doing the same operation over and over again. So as a quick exercise, suppose that I tell you that y is this function, 5x to the fourth minus x to the third plus 6x minus 1. And I want you to find these two things. I'm not even going to say them out loud, right? So hit pause and figure out for yourself what are those things. Get as far as you can. Okay, so I hope you have done that. One thing you need to realize is if I want to find the third derivative, in most cases, right, there might be some exceptions if you notice patterns, we're going to have to just do 3 derivatives. It's very hard to instantly jump from y to y triple prime. So we'll just go one at a time. So y prime would be 20x to the third minus 3x squared plus 6. That's my first derivative. Y double prime is my second derivative, 60x squared minus 6x. Y triple prime, my third derivative, is 120x minus 6. So that's one of my answers. Now this means the 33rd derivative. And one thing you want to file away is anytime you're asked something with a really huge number like that, probably you're not actually going to do all those steps. Someone's trying to figure out if you can notice a pattern. So let's maybe do a little bit more. My fourth derivative is 120. My fifth derivative is 0. And now, hopefully, we realize no matter how many more derivatives I take, it's just going to be derivative of 0 is 0, derivative of 0 is 0, derivative of 0 is 0. So I'm not going to write all of those. I am just going to use common sense and say, I know from here on out all of my derivatives are 0, so obviously the 33rd derivative is just 0. Anytime you start with a polynomial, eventually your derivatives turn into 0. And the number of derivatives you need is 1 more than the degree. So we started with something of degree 4. We needed 5 derivatives to turn it into 0. So this is relatively straightforward. You need to know what this notation means and be familiar with the vocabulary, but it's not hard. Now, in terms of why we care about this, some applications of higher derivatives really only come up in more advanced calculus. But we're going to see some examples in this class, especially of the second derivative. The second derivative is genuinely useful. In the near future, we will talk about how the second derivative is related to things we can see in a graph. But there's another example, another application of second derivative that we'll talk about right away. And it has to do with position, right? Motion problems. So we've already talked about this a little bit, but we know that if we have some function measuring position or height, the rate at which it changes is called velocity. So velocity is basically telling us how fast does position change, right? I'm moving. Am I moving slow? Am I moving fast? Velocity measures that for us. Now, acceleration is the rate at which velocity changes. So it's kind of related to whether things are speeding up or slowing down, right? If you're on the freeway going at 60 miles per hour, right, just constantly 60 miles per hour, you're not speeding up, you're not slowing down. Your velocity is very high, but your acceleration is 0, right? Because your velocity isn't changing. Acceleration would be, you would see acceleration greatly if you're changing your speed greatly, right? You're speeding up really fast or you're slowing down really fast. That's when we see a lot of acceleration. So kind of in our notation with calculus, position, often we call that s of t. There's a Latin word, I think, for position, something related to that. Maybe that is why it's s, but it's often called s. And so velocity, sometimes we just call it v of t, but the velocity function is the derivative of position. Velocity measures the rate at which position changes. And then acceleration, sometimes we call that a of t, that's the rate at which velocity changes, so it's v prime of t. But remember, v is already a derivative. So acceleration is the derivative of a derivative, and therefore it's the second derivative of position. Right, so velocity is the first derivative of position. And acceleration is the second derivative of position. And both of these are things that make a lot of sense to us, right? You have familiarity with moving, and I think you understand, when am I moving fast, when am I moving slow, when am I speeding up quickly, when am I slowing down quickly, when am I speeding up slowly, right? Acceleration and velocity are things that actually make sense to us. Acceleration typically is the result of some force acting on an object. So for example, when things fall, hopefully you know as they fall, they speed up. That's due to acceleration, and that's from the force of gravity. Earth's gravity is pulling on this thing, creating acceleration. Okay, so let's just do a quick example. And we're going to do this example on the moon just so that the numbers are different, right? If we do every problem on the surface of the Earth, we keep running into the same numbers because of how Earth's gravity works. So on the moon, we're going to imagine an astronaut is jumping up, and his height in feet after t seconds is given by this formula. I got this from the book. I'm going to assume that they actually calculated what it would be on the moon. Right? There hasn't been anyone on the moon for quite some time, so nobody has done this recently, but we're pretending it's happening. So what I want you to do is calculate the acceleration due to the moon's gravity. And then we're going to think about what are the appropriate units. Right, so hit pause and try to do this one on your own before I resume. Okay, so velocity is the derivative of this height function. So that would be negative 5.4t plus 27. And then acceleration would be the derivative of velocity. Second derivative of position, that's negative 5.4. So this number basically represents the acceleration due to gravity on the moon. And it's much lower than acceleration due to gravity on Earth. Right? On Earth, it's about 5 times as much as this, almost 6 times as much. Right? The moon is smaller, and because the moon has less mass, it actually has less gravitational pull. Now, what would be the units here? And here's where we really need to think about how rates work. So let's work through this carefully. So position in this problem is measured in feet. Now velocity is a rate. So it would be measured in feet per second. Time is measured in seconds here. Generally speaking, when we have a rate, there's a per in the units. Acceleration is also a rate. It's the rate at which velocity changes. So what we're actually going to do is we're just going to take this unit we had before and put a per second on it. When I ask the rate at which something changes over time, I'm going to take the units it had and just add per second. So this would actually be feet per second, which maybe feels really awkward, but that's what's going on because it's a rate of a rate. So it makes sense that we're saying per twice. The units for acceleration here would be feet per second. Now, sometimes people abbreviate that as feet per second squared, right? The idea is I'm doing per second twice. So people will sometimes use the squaring as an abbreviation, right? I don't want you to think that a second squared really makes sense. Time times time isn't really something we think about. Think of this more as an abbreviation, right? So when we're measuring acceleration, these are the kinds of units you're likely to see. Feet per second, meters per second, miles per minute, something like that. Okay, that's the end of this rather short section.